In linear programming problems, there are some which are to consider as spatial cases. And these are, we have the multiple optimal solution where there is a condition that the linear programming has more than one optimal solution. Another one is the redundancy, wherein the constraints does not affect the feasible region. And the other one is unbounded, that the condition for the objective function of the linear programming problem can be made infinitely large without violating any of the constraints. And for the last one is the infeasibility, wherein there's no feasible solution or feasible region occurred, then there are no points which satisfy all the given constraints. Now, as for our example, we have here for the multiple optimal solution, the given is to maximize the zj, which is equal to 6x plus 4y. And these are the given constraints: 3x plus 2y less than 18, x plus 2y greater than equal to 10, and of course the non-negativity constraints as x and y greater than equal to 0. Now, using the graphical method, we have to plot the given constraints by just simply replacing the inequality into equal sign. So the 3x plus 2y less than equal to 18 is now 3x plus 2y equal to 18. And for the x plus 2y greater than equal to 10 is now x plus 2y equal to 10. So using the intercepts, we can now plot the corresponding lines of these inequalities. Then from here, we can now test the given inequalities by using a testing point. So using the testing point at 0, 0, substituting that point into this inequality. So then for 3x plus 2y less than equal to 18 when x and y are zeros, so then 0 is less than equal to 18. The answer is yes. So from the corresponding boundary line, which is at 3x plus 2y equal to 18, so we have to shade the half-plane region of it, including the point of 0, 0. So this part of the half-plane region from the boundary line, which is 3x plus 2y equal to 18. And then for the x plus 2y greater than equal to 10, then we have to test using the testing point at 0, 0. So when x and y are both 0, so is 0 greater than equal to 10? The answer this time is no. So from the corresponding boundary line of x plus 2y equal to 10, then we have to shade the half-plane region of it, this time excluding the point of 0, 0, which is at the point of origin. And then obviously we have now the feasible region which containing these two different shades. And from here we can determine the extreme points. So obviously we have 3 points here. Then we can define them as P1, P2, P3. But obviously P1 and P2 can be determined right away because it falls exactly at the y-axis. So we can determine the Py at 0, 9 and P2 at 0, 5. Then we can determine the coordinates of P3 because it is a point of intersection between the lines 3x plus 2y equal to 18 and x plus 2y equal to 10. By just simply elimination method, we can eliminate the y by just simply subtracting these two equations. So we can find the value of x is equal to 4 and then substituting to another equation in order to determine the y, and we can determine the value of y as 3. Therefore, coordinates of P3 is at 4, 3. Then, finally, substituting the extreme points that we obtain into our objective function, then at 0, 9, the value of z is 36. At 0, 5, the value is 30. And at 4, 3, the value is 36. Now, since the objective function is to maximize the z, then we can consider the highest value. But it so happened that these two values are both 36 and higher than 30. Then we have two optimal solution here, either at 0, 9 and at 4, 3. So this is an example of multiple optimal solution because we can consider two extreme points. So we have one at 0, 9, and then we have another value at 4, 3. For the next case, which is infeasibility, this time we have to maximize the z, j, which is equal to x plus y, and given constraints, 3x plus 2y less than equal to 18, and x greater than equal to 7, then we have to consider also the non-negativity constraints here. Now, using graphical method, again, we can plot the given inequality by replacing the inequality into equal sign, and this will serve as the boundary line. And then plotting these lines by using the x and y intercept. So we have the line at 3x plus 2y equal to 18, and the other inequality, the corresponding line is x is equal to 7, which is obviously a vertical line. Now, the next step is we have to determine the feasible region by using the testing point. So for the inequality 3x plus 2y less than equal to 18, we can use the testing point, the 0, 0. Then when x is 0 and y is 0, we can have that 0 is equal to or less than 18. The answer is yes. Then from the boundary line, the corresponding boundary line of the inequality at 3x plus 2y equal to 18, we have to shade the half-plane region including the point of origin. For the next inequality, x is greater than equal to 7 at point 0, 0. When x is 0 greater than equal to 7. The answer is no. This time, we have to shade the half-plane region of the boundary line x is equal to 7, excluding the point of origin 0, 0. And then in this example, obviously, there is no common region. So we can say that there's no feasible region. And in this case, this is a case that there's no feasible region, therefore, no solution. So this is an example of infeasibility. Our next example is an example for redundancy, wherein this time we have the objective function as maximize zj, which is equal to 2x plus y, and the constraints are x plus y less than equal to 3 and x plus y less than and equal to 6, together with the non-negativity constraints as x and y greater than and equal to 0. So similarly, using the graphical method, first is we have to plot the given inequality by replacing the inequality into equal sign. So plotting these lines or sketching these lines by using or getting the x and y intercepts. So we can sketch the line as x plus y equal to 3 when x is 0, so y is 3, and y is 0, x is 3. So this is our line as x plus y equal to 3. And for the line x plus y equal to 6, the x-intercept is 6, 0, and the y-intercept is 0, 6. So connecting these 2 points, so we have this line x plus y equal to 6. And then for the next step, wherein we have to determine the area or the feasible region by testing the given inequalities using a testing point at 0, 0. So when x is 0 and y is 0 less than equal to 3, the answer is yes. So from the boundary line x plus 3, we will shade the half-plane region including the point of 0, 0, which is our testing point. And for the constraint or inequality x plus y less than equal to 6, so using the testing point at 0, 0, when x is 0 and y is 0 less than equal to 6, the answer is also yes. So from the boundary line, which is the corresponding line of the constraint, we have to shade the half-plane region of it, including the testing point at 0, 0. Then obviously in this case, which is a case of redundancy because we can delete the x plus y less than equal to 6, which does not affect the feasible region. And for the last case, which is unbounded, using our objective function that cj is equal to 2x plus y, and the constraints are x greater than equal to 3 and y greater than equal to 6, together with the non-negativity constraint that x and y are both greater and equal to 0. So graphical method, We can plot the given constraints by replacing the inequality into equal sign, and then we have here a vertical line x is equal to 3 and a horizontal line y is equal to 6. And then determining the feasible region by using a testing point. So for inequality or constraint x greater than equal to 3, when we substitute the point 0, 0, 0 greater than equal to 3, the answer is no. Then, from the boundary line, which is x equal to 3, we have to shade the half-plane region of it, excluding the point 0, 0, which is our testing point. Now, for the next constraint, y greater than equal to 6, so similarly, using the testing point at 0, 0, so when y is 0 greater than equal to 6, the answer is again no. Then from the boundary line, which is y equal to 6, we will shade the half-plane region of it, excluding the point of 0, 0 again, which is our testing point. And then obviously, this is our supposedly our common region, which beyond the given rectangular coordinate system. So this is actually an example of bounded to infinity because it's too large and it is beyond the given coordinates, rectangular coordinates. So we can say that this is unbounded to infinity. So this is an example or case of unbounded